especially in the seminar series of the Central Department of Physics. So this is more like informative, like informal talk. So if you guys have any questions during my presentation, please do not hesitate to ask me. So let's get started. So today's topic is one of the beautiful components of our cosmos, which we call cosmic dust. And I'm focused on the study of cosmic dust in the term galactic environment represent three distinct regions of our galaxy. The one is interstellar medium, which is the space between the stars. The second is high latitude clouds. So especially these clouds are located right above the galactic plane. So it's free of like background stars. So it's the best laboratory to study dust. And then the last one is the circumstellar envelope of a post-AGB star, which is an evolved star, like a dying star. So basically, I'll present my synopsis, regarding all these three topics in very short. And again, if you have any questions, please do not hesitate to ask me. So let's see. Okay, so let me introduce my collaborators. Dr. Aigen Lee, he's my supervisor since my MS, because he's one of the best, in dust. So that is the reason I don't want to leave him and work with somebody else. The second one is Dr. Bruce Train. He's from Princeton University. His expertise in dust. Mike Juvela, he's from University of Helsinki, Finland. He's experienced in observation. And basically he provide all of the data, if in case if we need those. Dr. Rainer Glacier, he's also from University of Missouri, Rolla. He's specialized in PAH, which is polycyclic aromatic hydrocarbon. And then Dr. Bibi Jiang is from Beijing Normal University, China, and she's expertise in evolved stars. So as an outline, so today I'll be talking about cosmic dust, like what is cosmic dust and why it is important to study. Then I'll talk about the dust in interstellar medium with the emphasis of 2175 angstrom bump, which is one of the mysterious absorption feature that we see in the interstellar medium. Then I'll talk about the dust in evolved star, which is again dying star. It has tons of mysterious feature like 2130 UIR. So I'll try to describe everything in very short. And then I'll jump to the dust in high galactic latitude, where I'll talk about the MBM and the diffuse infrared access cloud. And finally, I'll present my summary and future work. So the first question is, what is cosmic dust? Okay, so if you are not familiar, basically this cosmic dust is not equivalent to the dust that we find on the Earth. These are like very, very minute dust particles whose size varies from few angstrom to 1 millimeter in size, and they mix with the gas and dust particles. So if you see the structure of this dust, basically they are like non-spherical. And then it consists of like from few atoms to 1,000 atoms. So basically when I say few atoms to 1,000 atoms, that means I'm talking about the number of molecules. If you see the composition of this dust grain, at the center, it's a crystalline core, which is like more abundant elements that we find in our interstellar medium. So remember the three abundant elements that we find in the interstellar medium are carbon, silicon, and iron. So basically these crystalline core are made of those abundant elements. And these mantles are basically IC grain mantles. And the most important part of this dust grain is it provides the site for the molecule formation. So what does this point mean is, if we don't have dust in the interstellar medium, there will be no molecule formation. So basically dust help us to understand from atomic to molecular transition. So that's why dust is very important. Now, because many of you, you are like non-astronomers, so I just wanted to put this picture. So basically this picture represents the dark patch in the sky, which is also called a void in the space. This image was taken by Edward Barnard in 1919. and this is called Barnard 86. So basically, if you see this image, we don't, I mean, like this dark patch. So, I mean, initially they thought that this might be, like a hole in the heaven. Some people also thought that might be this is the way to the heaven. And then many people thought that there is no background star at all. So this was kind of mysterious image discovered by Barnard. But then when there was a launch of infrared telescope like Spiegel, and then you have like ISO, IRAS. So when those image was observed in the infrared wavelength, they revealed that the dense cloud of gas and dust is totally illuminated by the background stars. So if you see this image, so initial image was this, nothing was there. So basically they thought that it's a void, but when it was observed in infrared wavelength, you can see all the background starlights, right? So basically this revealed that the entire universe is like transparent for the infrared wavelength, okay? And then finally they revealed that these are the dense cloud of gas and dust. So the dust, cosmic dust, is very important because sometimes, some of the object is like totally, like obscured by these dust particles. And if we want to understand those obscured particles, we need the knowledge of dust particles. So again, the second thing is, why is it important to study the cosmic dust? So the basic answer is because the dust absorbs, scatter, and polarize starlight and re-emits it in the infrared emission. And if you calculate the total intensity of this radiation, it's like 40% of the infrared emission is absorbed and scattered by these dust particles. The second is to understand the origin and evolution of interstellar grain and their significance in the evolution of galaxy. So again, anything, whether it's evolution of a galaxy or formation of stars, planets, asteroid, or comets, everything, the basic ingredients for this formation is the cosmic dust for sure. And again, the most important part is the dust help us in the synthesis of complex organic molecules, which possibly leads to the origin of life. So my concluding point for this slide is all kind of celestial objects that you can think of, whether it's a galaxy, star, planets, asteroid, comets, anything you can think of, including life, they all are made up of cosmic dust. So we are indeed made of stardust. All right, so let's talk about the interstellar medium now. So I mean, everybody know what the interstellar medium is. It's basically the matter that exists between the two stars. Initially, people thought that the interstellar medium is like totally a vacuum. But that information is not correct. It's not vacuum, but it's filled with the gas and dust particles. But the density of those gas and dust is very, very low. So if you are talking about the density, is like 1 particles in 1 centimeter cube of volume. So that's the density of this interstellar medium. But then why does it matter? Like why these small fraction of element matter for us? The reason is because of the vastness of the space, right? So the space is so vast that these all tiny volume of dust particles make a significant contribution in the starlight intensity. So it's very important. Now the interstellar matter, basically when we say interstellar matter, basically we talk about the gas and dust grain, but I'll put more emphasis on the dust grain today. So the average size of the dust grain is like 0.1 micron. Now, of course, it can vary from a few angstrom all the way to millimeter. That's true, but if you are talking about the typical interstellar grain, the average size of the dust is indeed 0.1 micrometer. Now again, interstellar gas and dust is like 10% of the total mass of the Milky Way. So if you think about the total material of the Milky Way, 10% is interstellar gas and dust. Now again, remember this only include the baryonic mass. It does not include dark matter or dark energy. Now, in this 10% of the interstellar gas and dust, the interstellar dust is only 1% of the mass of interstellar matter. So that means 99% is in the gas phase and 1% is in the dust phase. But still, because of the vastness of the space, this 1% dust make a huge difference in terms of extinction, which is more like absorption and scattering. I will talk in more detail in the next slide. So again, this 1% of the dust absorbs, scatter, and reflects like about 40% of the starlight, which is like significant. So let's say if you're an observer and trying to do some kind of observation, and if you do not consider the extinction property from the dust, that means you're losing like 40% of the information in your data. All right, so the question is, what is the source of interstellar dust? So basically, there are like two basic sources. One I see is a star injection. That means all the dust is coming from the star. Now think about the cool star wind, like RGB or AGB, which is a asymptotic giant branch star. So if you see the AGB or RGB phase, this outer envelope is basically cool and extended envelope. And those dust are formed in these envelope. And finally, they are expelled in the interstellar medium. And if you see the amount, it's like 0.0025 solar mass per year. So this is the amount of dust that is injected from the cool star winds. The second is the planetary nebula. Now, everybody know what the planetary nebula is, right? So basically, when the star dies, the final stage of the star is nebula. So basically, the planetary nebula inject like 0.002%, which is kind of higher in compared to the cool star wind. And finally, the supernova. Remember, initially people thought that the supernova inject the dust in a very large quantity. But if you look at the destruction rate from the UV radiation, the supernova destroy more dust in comparison to the formation of the dust. So that is the reason, although the supernova, they make tons of dust particles, but they only inject like 0.002% solar mass per year in the interstellar medium. And the final is the formation in the ISM. And now people think that most of the dust are formed in the interstellar medium through coagulation or accretion. But then again, it's a very mysterious part. Astrophysicists are working still to find like where these dust are formed. Because if you add all the dust particles and compare to the observation data, still we are missing like 20% of the dust in the interstellar medium. And we have no idea like how those dust came into the existence. And by the way, I also put one picture here. It's called Betelgeuse. I don't know if you know this. So now, like few months before, the scientists, they thought that this gonna explode as a supernova within a week or so, because the intensity of this Betelgeuse, that reduces by 40%. But then finally, we realized that, well, the intensity was reduced not because of its activity of the supernova and stuff, but because of the dust particles. So it is enshrouded by dust everywhere. And this dust was the reason to reduce the intensity by 40%. And all those dust particles eventually will merge or injected in the interstellar medium. Okay, so let me talk about what the extinction is. So let's consider that you have a star, and this starlight is passing through the cloud of gas and dust particles. Now, you know that the blue light will scatter more in compared to the red light, right? So basically, this star will appear more redder in compared to the original star. So this effect is very similar to the effect that we observe on our Earth atmosphere, which is the blue sky and red sunset, right? And everybody knows this because blue light is scattered more in compared to the red light. So I just want to, make sure that you guys remember the term extinction, which I'll be using more often, is the sum of absorption and scattering. So when you add absorption and scattering effect, that together we call extinction. But again, there is the other term the astrophysicists use, something called attenuation. So attenuation is slightly different than extinction. So like half part of the extinction is attenuation, but when you talk about attenuation, they also include like like the additional starlight intensity from like third star as well. But we'll stick with the extinction. Okay, so this is one of the best example of the extinction that you can see in this nebula called Trivide Nebula. So if you see this red region here, I mean, it's more like a pink and a reddish color. This color is because of the ionized hydrogen. And then if you see this blue light, no, this is the original image taken in the, with the visible band, in the visible band. So this blue light represents the scattering of the blue color, and that was because of the dust particles. This is ionized, sorry, red color is from the ionized hydrogen atom. And then if you see this dark lane right here, so this dark lane are the dark and dense cloud, the molecular cloud that totally obscure the background starlight. Okay, so this is one of the best examples that shows both extinction, absorption, scattering, and together what we call extinction. So the question is, how do we find the extinction? So that this is the one easy way. So let's say the idea is what we call the pair method. So the idea behind the pair method is you take the two stars of same spectral feature. So basically they are like same star. The one star is passing through the cloud of gas and dust particles. So it will be redder because the blue light will scatter. And this passes, without any dust particles. So basically this star is more redder in compared to the blue star. Okay, and then the pair method, basically what it does is you divide the luminosity of this star with the radiant star. And when you divide those two, you get the curve, what we call the extinction curve. And this is how we calculate the extinction curve. So you take the spectrum of the red star, then you take the spectrum of the similar star, and then you divide the blue spectrum with the radiant star, and then you get the extinction curve. Now, there are other methods called color access and hydrogen recombination line, but the most reliable method nowadays, everybody they are using is a pair method because this is very easy. Now you can use color access method, but then, there are so many disputes going on that if the color access method gives you the exact extinction curve or not. Okay, the second thing is you also need to know the hydrogen column density. So basically, what is hydrogen column density? So let's say if you're looking at this star, okay? So when you're looking through this star, the line of sight, right? I'm just talking about this line of sight. So whatever the number of hydrogen is present on this line of sight, when you integrate all those hydrogen along this line of sight, that will give you the hydrogen column density. So it's confusing, with the name. We say sometimes we say number density, sometimes we say hydrogen column density, but hydrogen column density is one of the best way to study the extinction of dust. Okay, so again, hydrogen column density is the total number density of hydrogen in the line of the path. Okay, so let's talk about the extinction curve. So this figure represents the different sorts, and these are the extinction curve for toward those sight lines. So if you see this spectrum very carefully, the peak, the absorption peak of this curve is exactly at 2175 angstrom, which is like 4.6 inverse of wavelength. Now, if you see my axis, it's the inverse of wavelength. Now remember, it's an absorption feature. But it looks like an emission because we have used the inverse wavelength in the x-axis, just to make a very simple stuff. So the first time this 2175 bump, which is the very, very strong absorption feature that was observed in the interstellar medium, was like half a century ago, like more than 50 years from now. And these are like very strong feature. It's not like, like a weak feature. It's a very strong feature. If you see the peak of this feature, they are exactly the same 2175 angstrom bomb. So the striking characteristic of this, extinction curve is it has an invariant wavelength, okay? But the band, if you see the bandwidth is, the bandwidth of this curve varies to the different sight line. So the big question for, nowadays, um, you know, um, that we are facing right now is, what is the reason why this bandwidth of the interstellar extinction bump varies from one sight line to other sight line? It's a very challenging questions, and we are working to find the answer. And the important part is its carrier remains unknown. So even it has been like 50 years, that we discovered this extinction bump, but still we don't know what is the cause of this carrier. What element caused this, absorption feature? We don't know this thing. And this study focused on to find, at least we'll try to understand what might be the carrier of this feature. So this is again the extinction curve for our galaxy. The black line represents the average extinction curve. But I just want to give you an impression that in this curve, you need to understand few terms like a lambda is extinction at wavelength lambda. Okay, and then it is characterized by something called RV, which is total to selective ratio. Now the RV is very important while doing a study of the extinction curve, because RV will determine the nature of the interstellar medium. So for example, if your RV value is large, that means if the curve is flat right here, right? So that means it implies that the density of the interstellar medium is very dense. And possibly it has, they are made of a very large grain. Now, if the RV value is very steep, that means very low, that represents the diffuse medium. That means the density is very, very low. And then it is made up of more like small grain particles, which is less than 0.0 micron. So again, RV value, which is total to selective ratio, will determine the nature of interstellar medium. So basically, when you see the extinction curve, they will always represent with the value of RV, and that will tell you all the information regarding the environment of the interstellar medium. Okay, so now the 2175 angstrom bump is also and has also been seen in the distant galaxies. So I mean, if you see the like distant quasar, this bump has been seen toward the quasar. It has been seen in the UV attenuated galaxies. Damped Lyman alpha observer, which is like more atomic hydrogen in between the galaxy and the viewer, and those atomic hydrogen will create those kind of absorption feature. Gravitational lensing galaxy also shows the 2175 angstrom bump. And finally, the gamma ray burst host galaxies does show the the strong 2175 angstrom bump as well. So the target of putting this slide is the cosmic dust is present in the entire universe. You cannot escape the dust anywhere in the universe. So conclusion is the cosmic dust is more like omnipresent. Okay, so let me talk more about my more depth of my research. So the first thing that we work with this interstellar extinction was we selected like 16 sources along the galactic line of sight. And then these are the condition that has to be made. It must have a very strong 2175 angstrom bump. They have a well-known hydrogen column density, because if you want to, if you're trying to understand the carrier of this feature, it's important that you know this parameter very well. And then also these sources has already, they already have studied the gas phase abundances of carbon. Why I'm talking about the carbon, the reason is because most people thought that this extinction bump is from the silicon dust. Now, our group, we think that silicon is not sufficient in abundance to create this 2175 angstrom bomb. So our theory was that the carbon should be the, the carrier of this 2175 angstrom bomb. So we move forward, and then we are trying to answer these two questions. So what would be the likely carrier of 2175 angstrom bomb? So that's the main question we're going to answer. And then finally, whether the 2175 angstrom bomb strength is related with the carbon or silicon abundance. Now, as I told you, there are many astrophysicists that they debate that silicon. I mean, they have shown. I mean, in a good good journal, they have published like that the silicon shows the kind of correlation with the 2175 angstrom bomb. But then we disprove their theory, and then we try to show that, well, silicon is not sufficient to produce this bomb, but instead the carbon is the right candidate. So again, we model this source very accurately, and we derive the carbon and silicon dust abundances. Then we correlate the strength of this feature with both carbon and silicon dust. And then finally, we correlate the strength with the RV as well. Because remember, the RV will tell us if this extinction bump is made with a small grain or is made up with a larger grain. So we'll see all this kind of correlation. So the model we used was something called graphite and silicate dust model, which was designed by my advisor, Nigel Lee, and Professor Boostrin from the Princeton University. So basically, if you see, we use the two dust like graphite and silicate. So again, A lambda represents extinction at wavelength lambda, and H is your hydrogen column density. And then you integrate the extinction cross section, and then dN over dA is the dust size distribution. So we did for both graphite and silicate. And then we calculate the extinction cross section using the mean theory. I'm pretty sure everybody know what the mean theory is. And we use like N and K optical constant from the Drain and Lee paper. Again, this was the fit. So we fitted like very well. You can see the fit is very, very accurate. So we use all the absorption data. The red square represent the Fitzpatrick and Massa and CCM model. Green line is our model fit. And then if you see this blue line represents the extinction due to carbon dust. And then right here, the violet line represents the extinction from the silicate dust. So all of the sources we fitted like very, very accurately. And then the major thing that we did is we did check the correlation to see if the strength of the feature, which is the absorption feature, correlates with the carbon or silicon dust. So if you see the x-axis here, it's called C3 prime. So basically this is the strength of that bump. So I'm like the bump that you saw in the extinction curve. So what we do is we can use a Gaussian or any kind of software to fit that curve and then get the strength of the feature. So we correlate the strength of the feature with the carbon dust. And if you see the correlation, it's like kind of like a strong correlation. Well, it's not very strong, but still it shows a strong correlation with the carbon dust. So this is the carbon dust with the strength of the feature. Now, if you see the silicate or the silicon dust with this, the strength of the feature, that does not correlate at all. The correlation is like almost kind of zero correlation. So we did not find any correlation, with the silicon dust, but we find a strong correlation with the carbon. So this was, like a breakthrough, for our research. And then we thought that, okay, we presented in the seminar, like the, American Astronomical Seminar. And then there was some question that, if you use a carbon as an absorption feature, then hopefully they will correlate. So then we thought that, okay, this is not sufficient to, prove our point that carbon is the, carrier of this feature. So we also use like, okay, so we also use the second, so I'll come to this slide again. So we use the second type of approximation, which is model independent approach. So this is like nothing to do with the model. So we use a Kramer-Kronig relation. I don't know if you heard about this. So the Kramer-Kronig relation, basically they compare the total extinction with the total volume of the dust. Okay, so what we did is we found the total extinction by simply you integrate the extinction curve, you get the total extinction, right, from the observation. And once you have extinction, then you can find the volume of the carbon dust and the silicon dust. And then we also, again, correlated and see which one shows a correlation. And again, we found that the carbon dust does show some kind of moderate correlation, but the silicon dust does not show any correlation. Well, this both are for the carbon dust. Now, so when we do the Kramer-Kronig relation, the one problem is we have to assume the total cosmic abundance of the dust. I'm sorry, of the galaxy or toward the line of sight. So if you talk about the total abundance, it might be like the protosun or the B star, or some people take like solar abundance as a reference abundance. And then if you know the gas phase, so basically what I'm trying to say is the total abundance, right, is equivalent to the gas phase abundance plus dust phase abundance. So if you consider the total abundance, abundance as a solar abundance, and if you know the gas phase abundance, you can easily find the dust phase abundance. So basically, we were not convinced that the interstellar medium has a solar abundance. So we tried like both like proto-sun abundance and the B star abundance. And finally, we found that there is a moderate correlation with the carbon dust. And then we did not find, so let me go to the back slide. Yeah, so, and we did not find any correlation for the silicon dust. It's right here. Okay, and then finally, we also look at the correlation with the RV, which is total to selective ratio. And then even the inverse of RV shows some kind of, like a very moderate, but still a correlation with the carbon dust. And again, there is no correlation with the silicon dust. So this implies that, toward the far UV region, the far UV region of the extinction curve is made up of a very small carbon dust, more likely like a pH dust, pH particles. And there is no way that it is made of, silicon dust. So we disapprove the hypothesis that silicon dust is the carrier of 2175 angstrom bomb. And we indeed proved that carbon is the carrier of the 2175 angstrom bomb. All right, so that was all about the interstellar medium. So the second part I would like to talk is the dust in the evolved stars. So just let me give you a very short introduction. So this is the HR diagram, luminosity versus the temperature. And of course, this is the main sequence. So main sequence, so let's take an example of our sun is somewhere here. So right now, sun is cooking hydrogen into helium. And once the hydrogen is exhausted, the helium will start to burn, right? And then it will move to a red giant. Now, once the hydrogen will start to exhaust, this star, our sun will convert into something called AGB, which is asymptotic giant branch star, which is more like advanced phase of the red giant branch star. And then, in the red AGB star, you have a, like cool, dust at outer layer. And, because you have like some kind of super wind going inside the star, those envelope will, will merge in the interstellar medium in the form of something called planetary nebula. And finally, this planetary nebula will convert into the white dwarf. So this is kind of life cycle of the star. Now, when I'm saying planetary nebula, remember, this is one of the example of helix, my favorite, planetary nebula. So it's one of the beautiful picture that you can, find in our universe. So again, so these all dust particles, these, gas and dust particles, the envelope of these, planetary nebula will eventually merge in the interstellar medium, which will populate the dust particles, especially gas and dust particles. All right, so I'm not interested in planetary nebula or AGB stars. I'm interested in something in the intermediate, which is called post-AGB star. So which is a transitional phase between the AGB and planetary nebula. And why I'm interested in this post-AGB star, the reason is Okay, so so let me skip this slide. Okay, so the reason is they offer a pristine fossil record of stellar mass loss history. So it's like doing like carbon dating in the star. So looking at this post-AGB star, you can easily find what was the mass loss history while it was in the AGB phase or red giant phase. It will also help us to understand the symmetry formation. Now, if you see the AGB stars, so basically the symmetry is like more like spherical in nature. But if you see the planetary nebula, the symmetry is like axial, symmetry. So we're trying to understand what causes to change the spherical to the axial symmetry in this, planetary nebula. And then also we'll talk about the evolution of planetary nebula. And then the most important part is the chemical enrichment of the interstellar medium, what I'm, talking again and again. So these are the basic, parameters that inject the dust in the interstellar medium. So we are, these parameters are important. So again, if you see a AGB star, so basically this AGB and the post-AGB star has a central star right here, and it's surrounded by a circumstellar envelope of dust and gas particles. So if you see the SED, which is the spectral energy distribution, or you can say, spectra of this, AGB, post-AGB star, the first peak represents the central star, and the second peak right here represents the emission from the dust particles. Okay, and we are interested in this second peak, and I'll show you in the next slide why. But before I go to those spectral features, so this is the schematic diagram of dust shell of the post-AGB star. So if you see the center part is a star, this is what we call the superwind phase, which I'll talk in a minute, and the outer part is called AGB cell. Okay, now it's called AGB because this cell is coming, is continuously expanding from the AGB phase of the star. However, the superwind phase is more interesting. Why? Because this phase right here in yellow color, in red and yellow color, so it represents the end phase of the AGB star. So let's say when the AGB star die, the superwind, property is the basic way to, distinguish if the star is at the end phase of AGB or not. So what is superwind phase? So it's a very violent and catastrophic, explosion that explode at the end of the AGB phase. And then this will help to change the symmetry of from spherical to axial. So the first point we made is because of the superwind explosion and the catastrophic explosion is the cause of the change in the symmetry of this protoplanetary nebula. And then the second is we are also trying to understand what was the mass loss rate from these post-AGB stars. So this is the spectrum from the dust emission. So if you see this spectrum, wavelength versus this is the flux. So these are like very minute small features. It's called UIR. So it's called unidentified infrared feature. The second one is called the 21 micron feature because it is exactly in the 21 micron. And then this is around like 30 micron. Okay, so the 21 micron is one of the mysterious features that we can see in this evolved star. So why it is mysterious? Now remember, this was first discovered in 1989. It has been a long time. And it carries like 8% of the total infrared luminosity of the star, okay? And still we don't know what is the carrier of this feature. So that's the, limited part. The second feature is 30 micron feature. Again, this is also discovered by Forrest et al. In 1981. And it has been observed in carbon-rich star planetary nebula, and it carried like 30% of the total infrared luminosity. And again, we don't know what is the carrier of this feature. And finally, the UIR feature, which is called unidentified infrared emission feature. So this features was observed in like several bands, like 3.3 micron, 6.2, 7.7, and so on. And why it's called unidentified? Because at that time, this was not identified, like what is the carrier of this emission. But now, by to date, we are pretty sure that these are indeed from the PAH, which is polycyclic aromatic hydrocarbon. It's like benzene ring. So this part of the puzzle is solved, but still 21 and 30 micron meter and micron feature is still mysterious for us. So why are we interested in this source? The reason is because if you combine 21 and 30 micron feature, they emit like up to 40% of the total infrared luminosity, and that's a huge amount of luminosity. Again, the carrier of this feature is unknown, right? Even there, it has been more than 30 years of its discovery, and also help us to understand the condensation phase. So let's say if there was a formation of carrier, in what phase of this carrier it condense. So whether it's in the AGB phase or superwind phase, so that's the one question to explore. And then finally, we'll try to derive the accurate mass loss rate in AGB and superwind phase, which will tell us the entire history of stellar evolution. So again, our aim was, what would be the likely carrier of 21 and 30 micron feature, whether these features are correlated, what would be the carrier, and then in what phase of the stellar evolution this carrier feature was formed. So we tried to answer all these questions, and so this is the the model fit. So basically, we feed the spectra SED of these evolved stars. So I think we use more than like 30 sources altogether. So if you see the x-axis as a wavelength, flux, and you see these are the UIR, you have a 21 micron feature, and this is the 30 micron feature. So each and every post-AGB star shows all these three distinct features, okay? Green line represents the total model spectra, so that's our model fit. Black line represents the ISO data, that is the infrared space observatory data. Then blue line represents the dust features, are the features of the dust. The red line represents the thermal component. So basically we use like 2 temperature and the black body temperature to feed the continuum, below the continuum line. And then we also, the pink line should be somewhere here, represent the molecular hydrogen line. And you can see that we exactly fitted this. And again, we use the pH feed package. And I think we use the IDL, correlated at all. So 2130 and UR feature, that does not correlate at all. And this rules out the hypothesis of thiourea and aliphatic chain. So remember, like this guy called Poplar in 2000 and 2011, they proposed that the aliphatic chain and thiourea chain, which is more like sulfur organic materials. So these are the carrier of this 2130 micron feature. Now, if they are the carrier of this feature, right, then they should show some correlation because they are from the same dust particles. But we did not find any kind of correlation between these dust particles. So this rule out the hypothesis of this, a carrier of these thiourea and aliphatic chain compounds. And we already published this paper in APJ. We also found that the UR carrier result from the decomposition and scattering of 30 micron feature carriers does not support. So again, some people claim that the UR carrier, right, was result from the carrier of dust, or which caused the 30 micron feature. So those dust shattered and they made a 21 UR emission feature. So basically, we also disapprove the same dust particle that caused UR and 30 micron feature. It also rules out the large PS cluster as a possible of 21 feature. So these are like you have to go like very detail if you want to understand these results. But let me give a very concluding remarks about this correlation. So what we're trying to say is different people is telling that the same amount of dust, whatever the species of dust it is, they are causing all three features. Now, our proposal was if the same dust is causing all three features, then they should show some kind of correlation with each other. And that was the major breakthrough. And we did not find any kind of correlation, not even a moderate correlation. So this rule out all kind of hypotheses that was published in the past. And then we also did the dust infrared emission modeling. So basically, we try to understand the dust mass loss rate. We use all possible constraints that we can gather from ACARI, WISE, IRIS data, MSX, ISO 1.2 millimeter, which was one of the best constraint at the far infrared region. Sorry, yeah, far wavelength region. And then you can see we fitted very accurately and calculated the total dust in both AGB and superwind phase. And these were the correlation that we found. So we try to see the mass loss rate in the AGB phase. So basically this is the AGB phase right here. And this is the superwind phase, which is a more violent phase of the mass loss rate. And if you compare the 21 micron feature does show a strong correlation with the mass loss rate in both AGB and superwind phase. And then same thing with the 30 micron feature. There does show a moderate correlation for both AGB and superwind phase. So basically the concluding remark is the 21 micron feature correlates with the both AGB phase, but it does not show a strong correlation with the superwind phase. So basically if you see the correlation is like 59, that's not a very strong correlation, but again, still it's a moderate correlation. So we cannot like completely rule out, but still we can conclude that the carrier are condensed in AGB phase, but was not excited in the AGB phase. Because remember, when it was the AGB phase, you don't have a high intensity of ultraviolet radiation. So that might be the cause that it was there in the AGB phase, but it was not excited. And then we found that the 30 micron correlates with the MG and the superwind both, right? So as you can see right here, so they, here, so the 21 micron feature, and this is the, where is the 30 micron feature? Okay, so this is 21, yeah, so this is 30 micron feature. So 30 micron feature with the mass loss rate. And they also saw a very strong correlation in both AGB. And if you see the superwind, it is like 0.77. The Pearson correlation coefficient is like 0.77. So which is kind of, correlated. And we conclude that the carrier condensed in both AGB and protoplanetary nebula, which is like post-AGB star, and they get excited even by visible or infrared photons. Okay, and then the final part is the dust at a high galactic latitude. So this was like a very interesting part. So if you see, these are my sources. So this is the plane of the galaxy, and these clouds are like very, like above this. If you see, the latitude is like more than like 25 degrees. So basically we divide these clouds and this, line of sight into two parts. One is, we say it's called a high galactic latitude cloud. And the second one, we say a high latitude diffuse infrared cloud, an infrared cloud. Now, why we call diffuse? Because they has, if you compare their like intensity of infrared emission, the diffuse infrared has more intense emission in compared to the high galactic latitude. So basically we decided to divide into like two different parts. Although the properties are very similar, but some of the nature are totally different. Now, why we are using this studying these high galactic latitude clouds? The first reason is they are ideal for studying local interstellar medium. 200 parsec. Now, if you don't remember, 1 parsec is like 3.26 light years. So it's like a few hundred parsec. It has a very low extinction cloud. It's about like 1 magnitude. These clouds are like mostly translucent cloud. So that means the density is very low. And then it's like almost like gravitationally unbound. Remember, if it's a very tight, gravitationally bounded, then there is more likely to form a star. But these are like gravitationally unbound because it is very, very low density cloud. So this provides a very basic laboratory to study the dust and its properties. So, and these also again are the mostly free from background and foreground emission. So we don't have to worry about the reduction of the starlight intensity. So we have selected 120 MBM. So I think, so we already, submitted this paper for APJ. It's like 65-page paper. So it took a long time, to work on these two paper. And then the second one, the DIR, we choose like 81 sources. Now again, why we use these sources? Because they have well extinction. I mean, well non-extinction. It's like about 1 magnitude. They represent a variety of range of clouds. When I say variety range of cloud, that means they have the different form of like carbon monoxide and molecular hydrogen intensity. Some are very near, some are very far away clouds, and also their extinction varied from from a few magnitude to like 5 or 6 magnitude. You'll see in a minute. And the motivation of this was, to determine the properties of dust and what is the role of the dust, especially in the star formation. Now, if you know, the dust is a very basic ingredient for the formation of a star. So if you don't have dust, there will be no formation of a star. So we want to see the connection between the dust for properties and the formation of the star. So that was the major points we want to study in this one. Second is to understand the origin and evolution of dust in high galactic latitude. So what does this mean is what factor caused this dust particle to drift from the galactic center right above the high altitude. So we want to see like what is the mechanism, by what mechanism this dust was drifted to a high latitude. So that was the second point. And the third one is we also of course want to understand from the atomic to molecular transition, how the atom is converted to a molecular. And because they are very near and very diffuse cloud, more like translucent cloud. So this is ideal lab for astrochemistry. So these are the fit that we found. So basically this is for the MBM clouds. We use like 118 or 120 clouds. So this one is the IRS data. Again, the star represents the Planck data at 3 wavelength. And then we have a model fit. This of course represent the UIR band, which is more like pH. And then I don't know if you can see this right here, the triangle in blue color represent the modal integrated flux for the IRS and Planck band. So we have again exactly fitted all these constraints. And then this is for the diffuse infrared clouds. So for the diffuse, we found like lots of constraint. We use the DRB and Kobe, we use the IRIS, the Carey, Planck data, all kind of data. And then the green light here represents the starlight intensity, because we can also see some of the starlight intensity right here. So I think this cloud is more interesting because again, as I said, it has a good emission from the dust, and also it has some kind of starlight intensity. So we thought that might be this cloud is, I mean, in near future, it might form the, the protostar. So these are the results. I know it's a very complicated results. So these are the correlations. We found that all kind of like, emission from all wavelength band is showing a very, very tight correlation. It's a very strong correlation. So visual extinction, hydrogen column density show a strong correlation with far infrared emission as well. So this conclude that the major fraction of the extinction is from the large grain. Now remember, when you see this image, when you see this figure, people thought that this emission right here, which is, from the pH, which is polycyclic aromatic hydrocarbon. So they thought that these pH can only be caused, from the small dust particles. But looking at the correlation, that the hydrogen column density and even like the at 850 micron emission, they saw a very strong correlation, very tight correlation. And this shows that the major fraction of extinction is not from the small grain, but it's from the large grain species. So again, the presence of large cloud dust feature site, which represent the feature site for the star formation, because if you have a large coal dust, that means it's more likely to form a star. And these are the results. So that this histogram shows some more information like how the pH is distributed in this cloud, whatever the visual extinction, their column density. So we found all these kind of strokes. So majority of the cloud are in rich in pH abundance. So this is also, one of the mystery, how those pH was formed on those high latitude clouds. Majority clouds have low visual extinction, so that's good for us. And then also these clouds have low hydrogen column density. So that means the density is very, very low. Okay, so these are finally my summary. I just leave this for you guys. If you're interested, just send me an email or contact me, sir, and I'll be happy to post my slide. And then let me talk about my future work. So basically, right now, the fund that I got from the NSF. So basically, we are trying to unravel the elemental abundance of dust property in the interstellar medium. Now, what does that mean is, so many people, and when I say people, I mean the astrophysicists know that the carbon and silicon are indeed the abundant dust, components of our interstellar medium. But then if you see the observation data, the observation shows that there is a more abundant amount of iron particle as well. So the question is, what is that interstellar iron? And why don't we see those, iron in the form of dust? Now remember, the observation only finds the gas phase abundance of the iron, but the dust phase abundance of the iron is still missing. There are some other, like specimen like magnesium, sulfur, oxygen. So where are those dust gone? So this is a big, mystery, and we, especially I wrote this project to see if I can find and unravel the true elemental abundance, especially of the iron and magnesium of this interstellar medium. So hopefully I already started working on this project, and I'm planning to involve some student in the future as well. Okay, so the second part is the dust grain and its implication in the formation of star formation. So again, so we are trying to see how the dust grain is related with the star formation. So for example, if you talk about like the Tauri, like the protostar, so those stars, are like in the very early phase. So if you can compare the high latitude cloud, which is like a very diffuse medium, compared to the the cloud where you have a protosun, right? So if you compare those two kind of dust properties, it's probably more likely to find what is the correlation between the dust and the star formation process. So that will be my second project, and the third project is to model the large Magellanic Cloud, small cap Magellanic Cloud, using all kind of available data, whether it's IRIS, COBE, Spiegel, Herschel, whatever observation data we have. And then of course, the James Webb Space Wave Telescope, is coming next year. Hopefully that will also, provide some window for constraining these, these LMC and SMC. So we are planning to understand the extinction curve for these high latitude, large Magellanic Cloud and a small Magellanic Cloud as well. So thank you very much. And I'll be happy to take any question you may have.
Thank you. Thank you very much for this wonderful, as well as in the beginning, you explained why dust is important, and later you went through the interstellar curve, interstellar extinction curve, and what is the importance of extinction to study this sort of stuff. And of course, your result that you obtain, and also about your future work, you mentioned. Thank you. Thank you, Ajay, Dr. Ajay Mishra, for this wonderful talk. And now I would like to open floor, I should say, to all for the questions. And I would request Raju sir, if you are somewhere here, to cooperate me.
Yes, Binil sir, I am here.
Please, Raju sir,
Yeah.
if there is question in the chat box or.
Okay, thank you, Vinil sir. Yeah, thank you, Vinil sir, and thank you, Ajay, Dr. Ajay Mishra, for this nice presentation overview and also future scope. And particularly, of course, Binil sir said already, I am happy to happy further because of your interest in involving students or young people if they are interested in your work. That's very kind and nice of you. So
Thank you.
I now request if you have any question, please raise your hands so that of course, there are a few questions in chat already, which I will start with. But please raise your hand on the right side so that it will be easy to see who is the next in the queue. Now, please unmute yourself if you want to ask anything. But let me announce. Okay, mute yourself if you have. Okay, let me just mute if you are not speaking. So the first one who was in the chat already is Raju Lamsal. Do you have anything to ask, or is it only a comment? Raju. And then I will come to the Raju. Do you want to ask something? Or?
It's just comment, sir.
Okay, no problem. Next one is Raj Pradhan. Can you please ask Raj? Are you there? Raj Pradhan.
Sir. Hello, sir. Namaskar.
Yeah, please go ahead.
Can you hear me?
Yes, yes, we can hear you.
Okay. Thank you for wonderful talk. My question is related to, I saw some plots like this one, 21 and 30 micron only. But this feature is only you mentioned there. Can we see any other features out of 21 and 31 micron meter in post-AGB stars?
Just a moment. Ajay, sorry, you are muted. Just a moment.
Oh, okay.
Okay, okay. Now please start. Please start.
Thank you. So basically, we don't see any other feature beside these three basic feature. So the first, like the feature which has like a very small feature at different, wavelength band is from the PADs. Again, I already told you, it's from the polycyclic aromatic hydrocarbon. And then we have a very prominent feature, which is 21 micron. Then we have a 30. But beside these three features, we don't see any kind of, emission feature in this post-AGB stars. If it was there, we will definitely study for sure.
Okay, I have a next question. This is related to like this one age ISM and
is related with the stellar formation, right?
yes.
So basically, if you see the dust, now remember when you have a star formation, so let's say during when the cloud start to collapse, the temperature will start to rise, right? Now the temperature is so high that it will start to put a negative pressure on the gravitational force. So the gravity will not be able to collapse further so that they can start the nuclear fusion. So if there is no dust particles, there will be no further collapse. So basically the inward pressure and the pressure from the gravity will be balanced before nuclear fusion start. So there has to be a dust. So those dust, what they does is they will absorb the heat and they'll re-emit in the infrared emission. So that will decrease the temperature and the inward pressure, and the gravity start to collapse again. And then once you have a temperature of like 1 million Kelvin, the nuclear fusion start to they start the nuclear fusion, and finally that's what the birth of star. So basically we are trying to see how those dust the particles are related with the formation of a star, but just by comparing like two different density, one that has the protostar density and one that has a very diffuse density. And just looking at some correlation, we will be able to find what is the property of dust and what is the importance of dust in stellar formation.
I have a next quick question. Okay. So can I ask
okay,
my question?
And for the second question, for the metallicity of the galaxy, we don't worry about the metallicity because so metallicity basically represent like what are the metal components of those galaxies. But we are working with the interstellar medium, which is more like carbon, silicon, dust, and what is the extinction property? What is the value of extinction that this dust has effect on the observation of those galaxies?
I have a quick question, sir. What are the challenges to map the dust of our Milky Way galaxy?
We already mapped almost all kind of dust, so it's not challenging, but it's more like interesting, and the mapping of the dust can be done using like different. So if you know the gas and dust, if you see the correlation between the gas and dust, they are like very well mixed in the interstellar medium. So if you know the mapping of the gas particles, because you also know the nature of the dust particles.
Okay, thank you, Raj. Next one, I'm going according to the queue. So Leknath Subedi, are you there, Leknath? Leknath. Oh, okay. If not, maybe I request Ajay Kumar Jha, Dr. Ajay Kumar Jha, please unmute yourself, please.
Okay, Dr. Ajay, very wonderful presentation and very wonderful, very informative speech for all of us. I have so many queries. I'm also
Sure,
related,
go ahead.
yes, but due to limitation of your time, just I want to ask very few simple things. As you have studied the dust in very depth, dust, and have you studied the dust nearby the supernova explosion and AGB stars? Is there any differences between the dust properties nearby the supernova explosion and the AGB stars? Is there
Yes,
any
there is
difference
a,
between the
yeah.
properties
So
of
basically, when we talk about the AGB star, basically, as I talked, like the 2175, sorry, 2175 extra bump was one in the interstellar medium, and then you also have like 21 micron feature and 30 micron feature. But again, the carrier of those features is still unknown. So right now we cannot compare what was the nature of dust in AGB with the supernova. So, but simply we know that like these both inject the dust like carbon, silicon, iron dust particle in the interstellar medium. But during those phase, like during the before the explosion of the supernovae or like the AGB star when they converted to planetary nebulae, so basically we have no idea like what kind of difference in the dust specimen is there.
Okay, thank you, sir. And we have one other query. Just we are using gas, dust, gas, and dust. So there is no any difference between dust and gas.
No, I mean, there is a difference, but what we do is like, basically, if you see the interstellar medium, the gas and dust particles are very well mixed. So if you see the correlation, if you try to do the correlation of, the emission from the dust and the gas, they are like tightly correlated. So that means, it's a very famous equation, very famous, plot. That's so that our gas and dust is very well mixed. So if you can map the gas, that means you can map the dust.
Okay, thank you. Very nice information. And if possible, please leave your email ID because we are also doing
Sure.
the same work, like same like work. And
Sure.
and if there is any possibility to do work related to dust in Nepal from your
Of course.
side?
So, yeah, so that's what I was saying about to talk with Binil sir, that if we can collaborate with you guys, so that will be very great work. So yes, so of course we can work together and involve some TU students in this work for sure.
Thank you very much.
Okay, thank you, Dr. Ajay, and of course both Dr. Ajay, and of course Binil sir already is his MSc dissertation supervisor, and this is already his collaboration that exists.
Right.
So without delay, let me invite Devendra Raj Upadhyay, please, Devendra.
Okay, thank you, sir. Namaskar,
Namaste.
all of you. And thank you very much, Dr. Ajay Mishra, sir, for your very fruitful presentation. and related to your research work. Actually, I met your Professor Lee during
really?
IAU GA 2018
Okay.
at Vienna. He is very, very great person. I observed like that. And he has explained about evidence of graphene and nanotube in ISM at that time. And I
Correct.
impressed from his talk. And for this time, I want to ask few questions. Oxygen rich AGB star, silicon rich AGB star, we have found few data. I am also working with guidance of Professor Oral and Dr. Ajay Jha sir. We are doing few collaborative research work. I have done master thesis under the supervision of Professor Oral and interested to continue such type of work related
Sure.
to AGB star. So this talk is very fruitful for us and our group, and we are doing research work on this, just like IRAS 12 micron, 25 micron, 60 micron, and 100 micron, like that. In Akara band, just like wide S and wide L, and in that band, what type of work we can do using just like oxygen and silicon rich star data, AGB star data.
So you mean that? Okay, so basically, so you want like what kind of dust you can apply for those study, or like?
Yeah, yes, sir. Yes.
Uh,
What
so
kind of
so
properties, physical property we can find?
so remember like so these data like the IRS 2170, I mean like what you said, like the 4 band of IRS 60, 100,
Yeah.
25. So those micron bands will only tell you like what is the nature of dust particles, like whether it's a large grain or a small grain. So as you go to the far infrared, it's more like coal dust. If you go to the, like in the, the mid and low infrared region, it's more like warm dust. So basically these, infrared emissions simply tell you the, the nature of the, the size distribution of the dust particles. But if you want to understand the abundance of those dust particles, basically we have to analyze the feature, the emission feature from those dust particles. So basically you have to like, slightly, jump to the SED, absorption or emission feature, and then you have to try to analyze, to see if it's, from the silicon or from the carbon or, whatever, elements you want to work with.
Okay, thank you, sir. And my next question related, just like, please explain more about that. Is maybe the informative also. Please explain about graphene and nanotube in ISM. How it is possible? What is the evidence?
So basically right now, like observation has revealed that we do have such kind of, graphene, or you can say like carbon 60, which is also called bucky onion, right? So those kind of compound are present in the interstellar medium based on the observation data. But then we are not sure at this time because, even I was, one of the participant of that project with the Professor Ajay Lee. And the problem is, although you can claim that those bucky onion or graphene, is the cause of, those absorption feature, but then when you do the analysis of their abundance, so what you do is you find the total abundance of those elements in the interstellar medium. And when you try to calculate the emission from that amount of abundance, is not sufficient. So the abundance is not sufficient to emit that high amount